We're now ready to define the kinematic bicycle model, which is maybe the most prominent and most simple vehicle models. And it makes, amongst many simplifying assumptions, the assumption that there is no wheel slip. So the wheels are always moving like they would not slip on the ground. There is no sliding. Wheels can't move sideways, but the orientation of the wheels is always in the direction, in the velocity direction of the wheels. So this is a model that can be only applied to, let's say, slow parking motion, or to situations where you know that there is no sliding effect. But at high speeds, these models are less reliable. But they are very simple, and so let's look at them. We've said that a vehicle is considered as a rigid body because all the points on the vehicle don't move relative to each other. And so we consider the motion of such a vehicle as a rigid body around a rotation center. If we move that vehicle around that rotation center, if we rotate it around that rotation center, then we see that all the points that are on that rigid body move likewise around the rotation center. And they describe different circular trajectories of different radii. What we also observe is that the velocity vectors of these points are tangential to the circular trajectories, which means that they are orthogonal to the line that connects the rotation center and these points. And this is expressed here. The orthogonality is expressed here through these little squares. Now, the first assumption that we do with the kinematic bicycle model, and that's why it's called a bicycle model, is that we approximate the four wheels of the vehicle with just two imaginary wheels. And in many situations where we're interested in modeling the motion of a vehicle, this is actually sufficient. It's not sufficient if we want to control each wheel independently, like in the case of ESP, as we've seen earlier, but in a more general modeling sense, it can be sufficient. And that's why we are focusing here on this model, the kinematic bicycle model that approximates four wheels with two imaginary wheels, as illustrated here. So this is the kinematic bicycle model in its most simple form. But of course, we describe some of the quantities more precisely. The first thing to note here is that we make some very strong assumptions now. The first assumption that we make is that we only consider planar motion in the XY plane. So there's no roll or pitch of the vehicle modeled. There's only the heading angle, illustrated here by psi, which is the direction of the vehicle, this black line connecting the rear and the front wheel of the bicycle with respect to the x-axis of the coordinate system. And that's the angle here that we call psi. So we only model this planar 2D motion. The other assumption that we make is that we model only low speeds because we assume there's no wheel slip, which means that the orientation of these wheels is into the direction of the velocity of the point at the center of the wheel, indicated here by the velocity of the front wheel Vf and the velocity of the back wheel Vr, with the direction of these velocity vectors indicated by these two black vectors that face into the same direction as the wheels. Now, of course, in practice, we do have slip. Wheels don't move into the direction that they are facing. They can deviate quite strongly if you think about drifting maneuvers. But we are not considering this for the kinematic bicycle model. We're going to consider that later. Okay. So let's look at the other quantities here. Again, we have the rotation center around which these 3 points here, the rear center of the rear wheel, the center of the front wheel A, and the center of gravity of the vehicle are rotating. And through this assumption of no wheel slip, we also know that the velocity of that the rear wheel and the front wheel is into the direction of the wheels, which means that the wheels are actually also orthogonal to the lines connecting the rotation center and the center of the wheels. Similar to how the velocity of the front wheel and the velocity of the rear wheel are orthogonal to these lines. However, what we also observe is that the vehicle itself can indeed have a slip angle, a vehicle slip angle, and that is something that we denote here by beta. The vehicle heading is this angle here, it's psi. We already mentioned it. It's the angle of the orientation of that vehicle, the line connecting B and A with respect to the x-axis. But the velocity of the vehicle at the center of gravity, the velocity vector, does not point, in this case, into the direction that the vehicle is facing. But actually this point moves into a different direction that's described by the vector orthogonal to the vector or to the line that's connecting the center of gravity and the rotation center. Through the considerations that we made before, the rotation of a rigid body around a rotation center. Now, of course, here we have a very strong steering situation, which means that the turning radius is very small. And so the slip angle of the vehicle is rather large. But if you consider situations where you're driving maybe on a highway or you're driving straight on a parking lot, then of course the radius is much larger and the slip angle becomes much smaller, to the point where you might actually drive just straight, where the radius tends to infinity and the slip angle towards 0. So this is the slip angle of the vehicle. This is important to note. There is no wheel slip, but there is vehicle slip indeed, because the vehicle velocity does not point into the direction of the vehicle. What else do we have? Well, we have actually the orientation of the front and the back wheel, and that's called the front steering angle and the back steering angle, delta F and delta R. And those two steering angles are measured with respect to the orientation of the vehicle, as you see here. So we have this vector delta R and this vector delta F, which measures the orientation of the front wheel velocity vector, or alternatively the wheel orientation with respect to the vehicle orientation. In addition, we have LR and LF, which is the distance of the point B to the point C and the distance of C to A, and we call the sum of these two the wheelbase, capital L, which is the distance between the rear and the front wheel. And we call the sum of the heading angle psi and the slip angle beta the cos angle, which is basically the orientation of this velocity vector. This is in which direction the vehicle, that's represented by the center of gravity, is moving at a particular point in time. And of course we have to sum up psi and beta in order to arrive at the orientation of that vector. That's the kinematic bicycle model. And now we're going to use all of this in order to derive some useful equations, in order to derive how the vehicle moves. So what does this mean? What do we need to derive actually? Well, we want to derive the motion equations. We want to know how the vehicle moves and rotates over time. So what we want to know is the time derivative of the location of the vehicle, the location with respect to the inertia frame. We want to know the time derivative of the location of the vehicle, and we want to know the time derivative of the heading angle of the vehicle, which is also called the angular velocity. So we basically want to derive the velocities, and we want to derive those with respect to the quantities that we already know. And time derivatives we're going to always indicate in formulas with a dot on top of a symbol. So x dot means dx with respect to dt. Now, the first two equations here are simple. What is the time derivative? What is the velocity of the vehicle? Well, we know the velocity of the vehicle, which is v, and we also know the, as illustrated here, the cos angle, psi plus beta. So the velocity of the vehicle is simply v times cosine of the cos angle. And the y component of the velocity, so this is the x component of the velocity, the y component of the velocity is v, the velocity, times sine of the cos angle. So that's simple. But what is actually the expression for the time derivative of the heading angle, or the angular velocity in other words? Well, that becomes a little bit more complicated. And we're not going to show in this lecture the proof for this. So we're going to leave this as an exercise, because it's a simple extension of a proof that I'm going to show you for a simpler example, which is the case that we are more familiar with. A vehicle that's only able to steer the front wheel and not the rear wheel. Steering the rear wheel is something that can be quite useful, but it's not implemented in many vehicles. Most of the vehicles that we are familiar with can only steer the front wheel. While it would be useful to steer all the wheels, you could do much more dynamic maneuvers, and there is indeed also commercial vehicles available on the market that can steer the rear wheel a little bit in order to avoid drift, etc. But it's hard to implement in practice, and so most of the vehicles that we know, that we're familiar with, can only steer the front wheel. So this is the case that we're going to consider now, and we're going to call the front steering angle, because we have just one wheel steering angle now, delta simply. Not delta f, but just delta. And the rear steering angle is 0. Now in this case, the motion equations for the location of the vehicle stay the same as before, but the angular velocity simplifies. And we're going to derive this expression here. So how can we do that? Well, we do this through simple trigonometry. There's nothing more needed than very simple trigonometry rules. So the first thing that we'll consider is this red triangle here. And we note that the front steering angle, the front wheel steering angle delta, not only appears here, but because this vector is orthogonal to this line, and this line is orthogonal to this line, this angle also appears here inside that triangle. And what that means is that we can now express this relationship here, because of the orthogonality here, as the tangents of delta equals the wheelbase divided by what we call r prime here. This is the turning radius, and we call the radius the distance of the rotation center to the rear wheel, r prime. So the tangents of delta equals the wheelbase divided by r prime. So we can rearrange this to 1 over r prime equals tangent of delta over the wheelbase. We can also consider another relationship. First, we observe that similarly to before, this angle beta here not only appears here, but it reappears through orthogonality. It reappears also here inside that red triangle. And so the tangent of beta now is LR, this distance here, divided by r prime again. And so because we have already derived what 1 over r prime is, we can plug that into this expression here. So we get tangent of beta is LR times tangent of delta over the wheelbase. And you can see that now we have derived our first equation. We can also consider another relationship here, which is the cosine of beta, which is r prime divided by r. Rearranging this expression, solving for 1 over r, we get cosine of beta over r prime. And now plugging in 1 over r prime here. No, that's not what we do. So we get this relationship here. And now we consider the angular velocity, finally, which is indicated here by this blue circular arrow here, which is the rotation around the rotation center. So the angular velocity in blue is simply v divided by r. As we've seen on the previous unit, the velocity is simply the angular velocity times the radius. So this velocity here, the length of this vector is simply the radius times the speed with which this lever here rotates around the rotation center. The farther we are away, the larger that velocity is. So we see we have the angular velocity equals to the velocity at that point divided by the rotation, the radius, the turn radius r. Now we have just derived what 1 over r is, so we can plug that in here. So we have v cosine beta over r prime, and now we plug in 1 over r prime, and so we get v times cosine of beta over the wheelbase times the tangent of delta, and that's exactly the expression that we wanted to derive. So what have we derived now? We have derived the motion equations that relate the input quantities of our system, which is the velocity that we apply in our system. Actually, we only apply the acceleration, but that leads to the velocity in this simple model. And the front steering wheel angle, delta, this is the second input. So we have these two inputs here. And we relate this to the translational velocity of the vehicle and the angular velocity of the vehicle through these equations. And then, of course, if we integrate now, we can follow the trajectory of the vehicle if we integrate this expression. We can even simplify this further, actually. Now, this is the same schematic on the left as before, but what we consider is that the slip angle beta and the steering angle delta are small. So what happens in that case? First of all, when does this occur? Well, that clearly occurs when we're driving roughly straight. So only in those situations, this is a reasonable approximation. But let's see what happens in this case. Well, first of all, the beta here, because it's small, can be neglected. And the cosine of beta is, in approximation, constant 1. The tangents of delta, if delta is small, is proportional to delta. If you consider the tangent function, you will see that it's roughly linear at its origin. So you can consider this to be a constant, to be a linear expression, so be equal to delta. So what this means is that these expressions here simplify in the following way. So we don't need beta anymore because beta is 0 or close to 0, and it falls away here. And the cosine becomes 1. And the tangent of delta simply becomes delta itself. So this is the simplified expression. And here we can see again the tangent and the cosine function, where you can see that in the vicinity of 0, the tangent is approximately close to its is approximately equal to its argument, and the cosine is approximately 1. We can also derive a time discretized version of this model, where instead of the temporal derivative here, the time derivative, we consider discrete time steps, t, t plus 1, t plus 2. And in this case, the location of the vehicle at time step t+1, this is how you would simulate it on a computer for arbitrary small time steps, is the old location plus the a little bit into the direction of the velocity vector, and similarly for the heading angle. So we considered the bicycle model, but there's one thing that we have to talk about a little bit more in detail that concerns this approximation that we have made for the bicycle model, and that's the Ackermann steering geometry. The problem with the bicycle model is that if you now calculate or if you use the steering angle for the front wheel, if you would use that for both wheels, then you would necessarily obtain slip. And that's why in real vehicles, the front steering angle of the left wheel and the right wheel are never the same. And that's also the reason why there is a so-called differential on the rear axle that makes the two wheels move in different speed. So in practice, the left and the right wheel steering angles are not equal if there is no wheel slip. And this is particularly prominent if we make a sharp turn, if this rotation center is close to the vehicle. And you can see this already here. These two lines that connect, the line that connects the left front wheel and the rotation center, and the line that connects the right front wheel and the rotation center, are not coinciding, which means that the orientation of these two wheels must be different, because the wheel orientation, in the case of the kinematic bicycle model, must be equal to the velocity vector that's orthogonal to the lines connecting the rotation center and the wheel centers. So delta L and delta R are different. And the combination of admissible steering angles in this kinematic model is called the Ackermann steering geometry. If the angles are small, then the left-right steering wheel angles can be approximately computed as follows. Delta L is simply the tangent of L divided by R plus 0.5 times the track, the so-called track B, which is the distance between the two rear wheels. And delta R is the tangent of L over R minus 0.5 times B, which can in turn be, for small angles, approximately as L over R minus 0.5 B. In practice, the setup can be realized using a trapezoidal tie rod arrangement as illustrated here. Of course, the actual setup that's used in real vehicles is even a little bit more complicated than that, but it illustrates the matter of fact well. So you have this tie rod arrangement here, this trapezoid, that's used to steer the two wheels. And if you now move this arrangement a little bit to the right, you see that the left wheel turns much more into the left direction than the right wheel. And if you move it to the left, the opposite happens. The left wheel steers less into the right direction than the right wheel. And this is how the Ackermann steering geometry that fulfills these constraints of the kinematic model can be fulfilled or can be implemented.